protons, also 6 neutrons in the nucleus, and the positive charge of the 6 protons is balanced by the 6 electrons. Neutrons are very similar to protons, but they are electrically neutral rather than positive. So how did we learn about the nucleus of the atom? So we go back a little more than 100 years to Manchester in the UK. And Ernest Rutherford, Hans Geiger, and Ernest Marsden were scattering what's known as alpha particles from radioactive decay off of a thin gold foil. You might have heard of Geiger. The Geiger counter is named after Hans Geiger. And yeah, they didn't actually know what alpha particles were. They knew it at the time that they carried positive charge, but they didn't really know what they were. Right? We know now that they're basically a helium nucleus. So they were scattering these alpha particles just using a radioactive source. It was radium. And so they had a beam of these alpha particles off of a gold foil. You can think of aluminum foil, just more expensive. Most of these went nearly straight through, and this supported the current theory at the time, which was known as the plum pudding model of the atom. So people thought that there were negative and positive charges inside the atom. They already knew something about electrons. But they thought they were sort of equally spread and mixed, distributed more or less uniformly, the positive and the negative charges inside an atom. So they'd just sort of be a lump of material with these positive and negative charges spread throughout. And so they knew that they had this positively charged alpha particle beam, even though they didn't really know what it was. They knew it was positively charged. And so they said that, okay, if it was passing through the gold foil, and the positive and negative charges were spread out kind of evenly, then, okay, as the positively charged beam is passing through, it would be, close to some positive charge, but it'd also be pretty close to some negative charge. So it wouldn't get too attracted or too repelled, and it would go mostly straight. And that's what they saw most of the time. But then about 1 in 8,000 bounced back. And I think this is a really nice illustration of how important it is to perform an experiment many times, right? You think, all right, maybe they did it 5,000 times and everything looked like they were expecting. They would have said, we already did it 5,000 times. We confirmed this, we think we confirmed this sort of plum pudding model where the negative and the positive charges are spread throughout the atom 5,000 times. Well, that sounds like a lot, right? And so then then they did it 8,000 times or around 10,000 times, and they saw one, that looked like it went at a sharp angle. You did something, 8,000, 10,000 times, and you saw one thing that looked different from all the others. You might think you just made a mistake somehow. Maybe that was background. Maybe something happened. There was some glitch that you didn't know what was going on. So you'd have to do it, 80,000 times and see that happened 10 times, then go to 800,000 times and see that something bounced off at a sharp angle 100 times out of 800,000. So then you'd have enough statistics to say, oh yeah, it doesn't look like that first one, first time we saw something bounce off at a sharp angle was just a mistake or a glitch or something happened in the room or whatever. It really looks like it's about 1 in 8,000 that bounces back consistently once I do my experiment many, many times. So this was what it was bouncing off of, was the nucleus. And this was what led to the discovery that this prevailing model at the time, this plum pudding model of an atom, was not correct. But in fact, the atom was mostly empty space, right? And there was a positively charged core that then was repelling this positively charged alpha beam. And so, yeah, this is just rounded here. So this 1 in 10,000 here is just rounding to the nearest power of 10, 1 in 8,000. And then if you go to, so they were scattering off of gold, which has 79 protons and an total atomic mass, so combined number of protons and neutrons of 197 is the most common isotope, most common form of the element. And so it's actually much larger than just the hydrogen nucleus. So if you take the size of a hydrogen atom compared to its nucleus, the size of a proton, you get about a difference of 1 in 100,000, 5 orders of magnitude difference. So if you think of this in meters, the radius of an atom is about 10 to the minus 10 meters, sometimes called an angstrom. The radius of a heavy nucleus is about 10 to the minus 14 meters, and the radius of a proton is about 0.8 times 10 to the minus 15 meters. And if you think about this, 5 orders of magnitude. So if I put, let's say, a grain of sand in one end of a football field, so let's estimate the grain of sand. Our little grain of sand has about a size, a dimension, a scale of 1 millimeter, so 10 to the minus 3 meters. Now my football field, we're going to make it metric and make it 100 meters. So that's 100 meters compared to the 10 to the minus 3 meters, a millimeter, right? That's going to be my factor of 1 in 100,000. So if I put a grain of sand in one end zone of a football field, the electron, if I think of that as the proton, that's the size of my proton in a hydrogen atom. The electron orbiting that proton is off in the other end zone. So atoms are really mostly empty space. And I've cited a nice website here that I think I borrowed a lot of some of the images from my talk from this, and I think it's a really nice introduction, very accessible, particleadventure.org, to a lot of things related to particle and nuclear physics. So now we're going to skip ahead a little more than half a century to the late 1960s. So we had the technology at this point to scatter electrons off of protons at high enough energies to basically break apart the proton. And similar to the Rutherford-Marsden-Geiger experiment from the early 1900s, they saw that many bounced back sharply. This was done at SLAC, the Stanford Linear Accelerator Center in California. So when they looked at what was going on, when they sort of used conservation of momentum, which I'll talk about in a few minutes, they discovered that those electrons scattering off the protons weren't bouncing off the whole proton. They were scattering off of some kind of subcomponents. So this was the discovery that protons were not solid lumps of positive charge. And now the constituents that make up the proton, we call them quarks. And we don't really have a very good distance scale for quarks. They seem to be smaller than about 10 to the minus 18 meters, an attometer. Similar for electrons. So we haven't actually ever measured any like radius of the electron that was not consistent with 0. But it's constrained to be less than 10 to the minus 18 meters. Really small distances I work with. So the simplest model of the proton says that it's made of 3 quarks, 2 up flavored quarks and 1 down flavored quark. This quantity called flavor is actually the charge. It's what couples to the weak nuclear force that causes most radioactive decay. There are 6 different flavors of quark known as up, down, charm, strange, top, and bottom. So the first 2 known were up and down, and those are the ones that make up the proton. So the proton has 2 up and 1 down flavored quark, and the neutron has 2 downs and 1 up as the simplest model of the neutron. The third quark that was discovered was a surprise, and this was why it was named strange. Nobody was expecting it, so they thought there were some very strange things going on, and they called it the strange quark. But once they had these 3, they thought, we think that sort of by, since they saw that the strange quark was similar in some ways to this down type quark, they predicted there should also be a second one. These are heavier than these 2, and these top and bottom are heavier in turn. They thought there should also be a heavier quark that had some similar properties to the up quark, so they predicted this one and gave it a slightly more favorable name once it was discovered. So they called it charm. And then top and bottom were discovered later on. Top only in the mid-1990s, actually, when I was just starting undergrad, starting college. So these quarks that make up protons and neutrons are not completely free within the proton or the neutron. They are bound by force carrier particles that are known as gluons, and gluons were named after glue. I still haven't figured out who did that, but they were named after glue. Now there's something known as C quarks that's also present. These are short-lived quark-antiquark pairs that blip into and out of existence due to quantum mechanical fluctuations inside the proton. So if you think about it, so all atomic nuclei heavier than hydrogen, which just has one proton, but already helium has two. We said that protons have positive charge, so they should repel each other electromagnetically, and they do. However, the nucleus generally doesn't fly apart, except for some very heavy elements where you have radioactive decays where they do fall apart for various reasons. But many atoms are stable. So how do we overcome this electromagnetic repulsion among the protons in the nucleus? Well, it's because protons and neutrons interact via the strong nuclear force carried by gluons. And so the strong nuclear force interacts directly with the quarks. And it's kind of since protons and neutrons are already these bound states of quarks, it's actually more like if you've already studied something known as the van der Waals force in chemistry. So it's a residual interaction where you have electrically neutral atoms, but you can still have some electromagnetic interaction that leads, the van der Waals force still leaves some residual electromagnetic interaction so that it can affect chemistry, affect atomic interactions. It's the same idea with the protons and neutrons. So the protons and neutrons are the neutral, if you will, neutral with respect to the strong force, bound states, because it's the quarks that are carrying the charge that couples to the strong force, which we'll talk about in a second. But then there are these van der Waals-like forces, these residual forces due to the strong force that ends up holding the nucleus together. So that binds the protons together and the neutrons together, all of them. It's much stronger than the electromagnetic force, about 2 orders of magnitude, about 100 times stronger. And it's way stronger than gravity, so about 10 to the 38 times stronger than gravity, thus the name, the strong force, sometimes also called the strong nuclear force. But it has very short range of about 10 to the minus 15 meters. Remember, the radius of the proton is about 0.8 times 10 to the minus 15 meters. And so even though this is a really strong force, it only interacts over really tiny distance scales. So what property does a particle have to carry for the strong force to act on it? It's known as color charge. Quarks carry color charge, plus the gluons themselves. Gluons are the force carrier particles that will bind the quarks together. So gluons play a role similar to photons in electromagnetism. So electrically charged particles are actually repelling or attract each other by exchanging photons. But photons don't carry electric charge. They're electrically neutral. So this is a big difference between electromagnetism and the strong force, that the force carrier particle of electromagnetism, the photons, don't carry electric charge, but the force carrier particle of the strong force, the gluons, do carry strong charge, known as color charge. It's called color for the strong force because people saw back in the 1970s when they were figuring out the theory of the strong nuclear force, they saw that they needed 3 different charges to combine to make something neutral. And they thought of the analogy to red, green, and blue light making neutral white light. So when it's called color, I mean, it has nothing, the only thing it has to do with color is that you have 3 to make a neutral, 3 charges to make a neutral. And so again, this is different from electromagnetism, where we have just 2 things to make something electrically neutral, 2 different types of charges. We just call them plus or minus, positive, negative. And until I studied the strong force, I didn't really think about it. It seemed so obvious, so intuitive. Like charge for me just really meant electric charge. And it was really strange to me to think of having 3 different charges to make a neutral instead of 2 different charges to make a neutral when I first started learning about this. So then the theory describing the strong force is known as quantum chromodynamics, chromo because of this color charge that people decided to name it for 3 charges making a neutral. Quarks do also carry electric charge, and they carry fractional electric charge, which I think is really neat and I think has some deep meaning that we haven't understood yet. So I told you that the 3 main quarks of the proton are known as up, and down quarks. So the up quark carries positive 2/3 electric charge, the down quark carries minus 1/3. So to get the total charge of the proton, we have 2/3 plus 2/3 minus 1/3. So 4/3 minus 1/3 equals 3/3. And we get the +1 charge of the proton. The neutron instead, the primary quarks are down, down, and up. So minus 1/3 plus 2/3 equals 0 electric charge. So these 3-quark model, the simplest picture of a proton or a neutron, these are actually called valence quarks. So analogy, if you've studied the valence electrons in chemistry. Yeah, so it's a similar concept to valence electrons in chemistry. Typically the valence electrons, the ones in the outer shell of an element, of an atom, are the ones that determine a lot of its chemical properties. So like these are the columns of the periodic table, have a different number of electrons in their outermost shell, basically. And they determine the main chemical properties of an atom. So these are known as valence quarks, and they determine the main the quantum numbers, the total charge, and some other properties of these particles. They determine the main properties of quark-bound states. So we actually never see quarks or gluons directly. They're confined to composite color-neutral particles. So this is actually known as confinement. So we can have groups of 3. So in any instant, one would be red, one would be green, one would be blue. And these are called baryons. Bary being a Greek root that means heavy. Or quark-antiquark pairs. In any instant, the quark would have one color, say red, and the antiquark would carry an anti-color, actually, so anti-red. These are called mesons, meso for middle, in this case, middle weight particles. There are things called leptons for lightweight particles, but those are actually, they include the electron. They don't interact via the strong force. But at the time, people didn't understand all of this, so they had their heavy, middle, and lightweight particles, and they were still trying to figure out how to categorize them and how they interacted. So when you think about, remember I said before that the gluon carries color charge itself, which is different from the photon. So if two electrons exchange a photon and repel each other because they're both negative electric charge, that photon, because it doesn't carry electric charge, it can't change. You can't change the electric charge of any of the particles it's interacting with. But gluons, as I mentioned, do carry color charge. So gluons can change. They can give that sort of exchange the color charge with the quarks it's interacting with. And so I said before, it'd be any instant. So unlike think of an atom as an electromagnetic bound state, the electron is always negatively charged. The proton is always positively charged, right? They're not swapping charges. This is different for the strong force, because in one instance, the down quark in the proton might be red, but along comes a gluon from, exchange between one of the other quarks, and then it changes it to green and has to correspondingly change one of the other quarks to red, so that we keep something that's overall red, green, blue, and neutral. So this is also a very different feature of the strong force, and it's related to the fact that the gluons carry charge themselves, unlike the photons, which are neutral. So if you do try to pull two quarks apart, the energy between them increases until you produce a new quark-antiquark pair via equals mc squared. So you can think of this like stretching an elastic band. As I'm stretching an elastic band, I'm storing potential energy in that band. And the more I stretch it, the stronger the force is trying to pull me back. And so here we have basically a gluon field, a color field between the two quarks. Here it's drawn as a charm-anti-charm pair, or a charm and anti-charm quark that are being pulled apart from one another. We have this potential energy field between them that's storing more potential energy the farther I pull it apart, just like the elastic band is storing more potential energy the more I stretch it. And then at some point through E equals mc squared, we convert that potential energy stored in the color field, the gluon field, the strong force field, so like an electromagnetic field, but a strong force field, and convert it into mass via E equals mc squared. And then we can produce a new quark-antiquark pair. So here it's a down-anti-down pair that is produced. And then they end up binding. the new ones that were just produced end up binding to the original ones, and then you form new bound states. Here, these are these middleweight particles, mesons, that carry a quark and an antiquark. In this case, this is known as a D minus meson. Minus is the electric charge. So it's got a down and an anti-charm. And the partner here is a positive electric charge, D meson, which the valence quarks for which are an anti-down and a charm. So one of the overarching questions in my research is, how do we understand the protons and neutrons of the atoms around us in terms of the fundamental quarks and gluons described by our theory of the strong nuclear force, quantum chromodynamics? So I just told you can't see individual quarks and gluons because they're confined into these bound states. So if you can't do this, how do you determine the proton structure? How do you determine what's going on with the quarks and gluons inside the proton? In general, what we do is inelastic scattering. We shoot a high energy beam, for example, of electrons. You can use other particles. We shoot a high energy beam at the proton to break it up, and we try to understand what happens. If we use an electron beam, the electron doesn't carry any color charge, but of course it carries electric charge. And it'll exchange a photon with a quark because those quarks carry that fractional electromagnetic charge. So the quarks also interact electromagnetically. So if I have my electron beam, I have my proton. I've just drawn a simple picture here with only 3 valence quarks, the ones that determine the proton's main properties. So the electron ends up scattering off of one of the quarks, right? So we have inelastic scattering with the proton. We end up breaking up the proton, but it actually ends up being elastic scattering with one of the quarks inside it. Because it's elastic scattering, and because I know the initial state electron beam momentum, and I can measure the scattered energy and angle of that scattered electron, I can just use, so I have 2-to-2 scattering in the end, two bodies coming in, 2 bodies coming out, elastic scattering, and I can use conservation of energy and momentum to infer information about the quark in the instant it's scattered from within the proton. So I work at these really, really tiny length scales, and wanted to talk a little bit more about how we do that, how we get probes sensitive to different length scales, or how to think about probes sensitive to different length scales. So if you, I've lived in Michigan now for 8 years, and I really like living in Ann Arbor, Michigan. But one of the things that I don't like compared to basically all the other places I've lived are the roads. The roads just have a lot of potholes here. And so, if you think about being sensitive to different length scales, so you can ask the question, what size potholes will bother you if you are driving or riding different vehicles? So if you go to do your grocery shopping using a tank, right, you're not, the treads on your tank are so long, you're not even going to notice there are potholes in the road, right? You even if you wanted to use your vehicle to detect those potholes, you wouldn't even be able to. You'd be insensitive to them. You wouldn't even feel them. So ones that your tank to go do your food shopping would not even be able to detect, wouldn't be sensitive to. Your car could be a problem for your car because of the length scale of the car wheel, right? The tire on the car is much shorter than your tank treads that extend over the whole vehicle. And then if you've ever seen people with jogging strollers instead of like regular strollers, and notice that they have bigger wheels. So this is for a reason. This is so that not every little hole, little crack, etc., will bother you while you're trying to run, right? You don't want to be paying, if you're trying to go out jogging while you're pushing your kid, you don't want to be watching for every little hole, every little crack in the sidewalk or whatever. So you've got these bigger wheels that are going to be less sensitive to what's features on the road and the sidewalk. If you're out on your skateboard, you've got a really good pothole detector. You can detect really small potholes with your small wheels, right? So you're not going to just roll over them. So any hole that's a similar scale or larger to the size of your skateboard wheel, you're going to feel it, and you got to be careful. So I use basically short wavelengths, right, to detect, to resolve features that are at the scale of the wavelength or larger. So I'm not going to be able to resolve things that are smaller than the wavelength of what I'm using. So we go to higher energies, they correspond to smaller wavelengths. So if you think of just the electromagnetic spectrum, and we have radio waves with 1,000-kilometer wavelength, um, microwaves. There's a big jump here from a kilometer wavelength to centimeter wavelength, but infrared visible light, ultraviolet, X-ray, and gamma rays. So we're going up in energy. And here are the size scales that correspond to the wavelengths of these different frequencies, different wavelengths, different bands within the electromagnetic spectrum. So, yeah, as we're going down, if you've done maybe in ninth grade biology lab, if you used microscopes to look at cell structure or protozoans, microorganisms, you can do this using just visible light, because the wavelength of visible light is smaller than the size of cells of a cell, of a single cell. And so it's got the right scale to be able to do this. If you want to study, molecules, you can't use visible light. You're going to have to go to something that's shorter wavelength, like ultraviolet light. If you want to study atoms, you're going to have to go to even shorter wavelengths, X-rays. So remember, the size of an atom is about 1 angstrom, 10 to the minus 10 meters. This is the wavelength scale of X-rays. So they allow you to see features at the atomic level. And then I would need to go to even shorter distances that would only be available through gamma rays. And unfortunately, we don't have, so there are, hang on. So we do study the molecular, I don't, but the scientific community studies the molecular and atomic structure of matter using ultraviolet light for molecular structure. So wavelengths range from about 10 to 400 nanometers. So this is the right scale to be able to be sensitive to molecular structure. If I want to go to atomic structure, I need to go to higher energies, to X-rays, so shorter wavelengths, so about 0.01 to 10 nanometers. And then I'm going to be sensitive to features at the atomic scale. So nuclei and protons, we said they were like 10,000. 10,000 was like the 1 in 8,000 that bounced back off of a gold foil, gold heavy nucleus, to 100,000 times for a single proton, like a hydrogen nucleus, smaller than the size of the whole atom. So we need high energy particle accelerators to see inside them. So there are, to study molecular and atomic structure of matter, they actually have facilities. There are several in the United States, and usually there's sort of a few per continent. So they're big facilities used by thousands of scientists who come there to do their research, because they aren't the kind of facilities that you would have in a university lab. So yeah, there's out in California, they have one in Chicago, outside of New York. I guess are the 3 I think that we have in the United States that are called synchrotron light sources. So they actually accelerate electrons and then make them curve around to basically change direction. And when the electrons change direction, they emit photons. And they can control the wavelength of the photon. So they these facilities get to high intensity ultraviolet beams and high intensity X-rays. And people can bring their like crystal samples or biological samples or whatever, and put them at the end of the beam line with these photons that are being emitted off of an accelerated electron beam to study their samples. We don't yet have the technology to do this with such high energy photons with gamma rays that I would need. And so I need to use different techniques. I can't just bring my sample of protons and stick it at the end of like a photon beam line, a gamma ray beam line, because we don't have the technology to do that. So I use other types of high energy particle accelerators to see inside them, taking advantage of what's called wave particle duality in quantum mechanics. So what the internal structure of the proton looks like depends on what energy, or equivalently, we said energy corresponded to wavelength. And so what distance scale that you probe it. And so if I just have wavelengths that are of a similar or larger scale than the proton radius, I'm just going to see the proton as a whole. And if I have something that is sensitive to, some kind of distance scale a little bit smaller than the proton, I'm going to be sensitive to this 3 valence quark structure. If I have really short wavelengths, then I'm going to be able to access these anti-quark pairs that are being blipping in and out of existence due to these quantum mechanical fluctuations. So I work at 2 facilities. One is at the Relativistic Heavy Ion Collider at Brookhaven National Lab on Long Island, New York. I work at the Phoenix and S-Phoenix experiments there. And then I work at the Large Hadron Collider at CERN in Geneva, Switzerland, as part of the LHC Beauty experiment, Large Hadron Collider Beauty experiment. The Relativistic Heavy Ion Collider is the only active particle collider in the United States. It's on Long Island, New York. So this is a satellite view. You're not actually seeing the accelerator, you're seeing the access road for cars to drive around it. And this is Manhattan over here, Brooklyn and Queens. So it's further east on the island where Brooklyn and Queens are, like an hour and a half, 2 hours outside of New York City. Now here's an aerial view of the accelerator complex, basically. By 2030, it'll be transformed into a new facility known as the Electron Ion Collider. So yeah, I'm in the leadership of this group, part of the 10-person steering committee that's been working toward this for, on part of that leadership for the past 4 years. And the first time I actually got involved, the first time I gave a presentation, I was a student in 2002 at a workshop dedicated to trying to make this facility happen, was in 2002, so 18 years ago already. And it was really exciting earlier in 2020 that it was announced by the US Department of Energy that they are going to build it. It's about $2 billion. And it will be sited at Brookhaven National Lab. There was another place that was a candidate for siting this. And they announced in January that they will be building it and that we're going to build it at Brookhaven National Lab, which is really exciting. So for $2 billion scale facilities, these are really unique facilities worldwide, typically, or this is going to be a completely unique facility worldwide. It takes a long time and a lot of people who, so there's a community of more than 1,000 scientists. 32 countries are involved, where scientists from 32 different countries, from 238 universities and laboratories in these 32 countries that have already, said, written their names down. We want to be part of this facility. So I think it's really exciting to be part of international science, these big projects. And it's something I really appreciate about the work that I do, that I have opportunities to interact with people from around the world and to see how science really transcends political boundaries. So, we have people from rival countries that are involved on the same experiment, working shoulder to shoulder. And it's just so really different than just reading about reading things in the news, really working with people from all over the world and being able to ask them in person, what their views are and what's going on in their country. Yeah, so I really like that aspect of my work. So at the Relativistic Heavy Ion Collider, so this facility isn't built yet, but it will add an electron beam to the existing facility that's already there now, that's been running since the year 2000. I started working at the Relativistic Heavy Ion Collider. Well, at first, actually, I did it as a college, during college, the summer after my sophomore year in 1997. And then ended up going back there in 2001 and have been working there since then. So these are big facilities, but they're really long term, right? So this facility, the Relativistic Heavy Ion Collider, was also about a $2 billion facility. And it's been running for since 2000, so 20 years already. And it will run until 2025, and then it'll stop running so that it can be upgraded to add an electron beam and create this new facility. So they're long-term investments that end up being used by thousands of scientists from around the world. So this is really a great facility to study protons and the strong force. So what systems are we studying? We're studying protons. It's my main focus. And we can polarize them. I'll talk a little bit more about spin, the quantum mechanical property spin in a couple slides. We're also studying nuclei. You can see my picture of the proton here is now a little bit more complicated. I didn't just draw those 3 valence quarks because the research we want to do at this facility goes beyond just studying those 3 valence quarks, so looking also at the quark anti-quark fluctuations, looking at spin momentum, correlations inside this. So we want to study this in a lot of detail. We're studying nuclei. I don't have a picture that was the quarks and the gluons in the nuclei, but we're studying the quarks and the gluons in the nuclei. And we're studying nuclear matter so hot and dense that the quarks and gluons are briefly deconfined, so they're not in bound states anymore. Doesn't mean that I get to see them individually, but basically they're in it's a plasma. It's analogous to an electromagnetic plasma, which you probably haven't studied. It's not typically studied in high school, but plasma, an electromagnetic plasma would be where you have so much energy. You can think of such high temperatures that the electrons can't stay bound to the atoms, but they're still nearby. So the whole plasma is electrically neutral, but the electrons are separated from the atoms. So this is like when you see lightning, it's ionizing the air, and you have for a split second a plasma created by lightning, for example, electromagnetic plasma. This is the strong force analog. So we have a quark gluon plasma. So we're not really taking out a quark or a gluon. We're just making the temperature so hot that they can't bind for a split second into these bound states. And we actually, so my experiment at the Relativistic Heavy Ion Collider, Phoenix, which I'll talk about in a second, we were in the Guinness Book of World Records for the hottest temperature ever created on Earth. It is hotter than the core of a star, for example. And then, so my other facility, the Large Hadron Collider, but an experiment that I'm not part of there, actually beat us like a year later. We weren't in the book for so long, which was kind of disappointing, but it was the same idea. So they're also creating a quark gluon plasma. So the highest temperature certainly ever created on Earth, and the highest, as far as we know, it's the highest temperature currently in the universe. So you'd have to go back to the last time this state of matter, quark gluon plasma, is believed to have existed naturally. It is about 10 microseconds after the Big Bang. This is the last time it was hot enough for the quarks and gluons to be deconfined. And of course, it's super, super tiny, right, in the laboratory, and it's only for a split second. But we can measure the way we measure, one of the ways we measure the temperature is by looking at the energy of the photons that get emitted from this. If you've ever studied why like a hot piece of metal, well, if you heat it enough, it'll glow orange, like maybe in your toaster oven or something. You can see the metal glowing orange. This is thermal emission of photons, and the color when it's a visible color. So sometimes you can see when it's in a certain range of energy of the photons, we can see it as visible light, right? We can't see infrared, we can't see ultraviolet, we can't see gamma rays with our eyes. We can see when it happens to be the right temperature to be in the visible spectrum, like that glowing orange metal. So it's the same, and if you look at the color or just the frequency or the wavelength of the light being emitted by something hot, you can tell what the temperature is. And so we use that technique to look at these really, really high energy gamma rays that are emitted from the quark gluon plasma to infer the temperature of the plasma, just the way that you could, if you had the equation handy, you could infer the temperature of that glowing metal in your toaster oven by carefully analyzing exactly what color it was. So the facility has 2 colliding beams of ions, so they're counter-circulating. So the whole thing is it's a big circle. It's 2.6 miles circumference, 3.83 kilometers. And we call it heavy ion collider. So, but we do hydrogen ions, so protons, which of course is not heavy. That's the lightest possible atom, lightest possible nucleus, through uranium nuclei is the heaviest we've ever run. And we call them ions because, so So, okay, an ion is an atom with not a balanced number of electrons. You can have ions with extra electrons or with too few electrons. We strip all the electrons off the atom. So this isn't really a chemist's ion. These are bare nuclei. We just thought that the public might be scared, people living nearby, if they heard that there was a nuclear collider in their backyard. We thought an ion collider might sound a little more comfortable for them. We just, they're ions with all the electrons taken off, which I would call a nucleus, but it is technically an ion. So yeah, it's been running since 2000, like I said. So this is the 2.6 mile radius. So here's the ring road. This is where you drive to access. Here are the buildings where the experiments are housed. And there are two main experiments there. There were some smaller ones that are no longer running. So this is the one I've been on since 2001. This is the one I worked on in college just for a summer in 1997. It's about 1,000 scientists involved coming from universities and laboratories around the world. So on Phoenix, 14 countries are involved from 73 different institutions. And we have about 500 participants. And this is only a small, when you have 500 participants from 14 countries, when you try to take a group photo, we never have a meeting where everybody shows up. I mean, usually it'd be maybe a couple hundred out of the 500 at any given meeting that they all manage to travel to Brookhaven National Lab in New York. So this is not even half the collaboration in this photo, but here I am holding the sign in the middle, looking, I guess, 14 years younger. This is a 2006 photo. And this was when we first reached 1 billion collisions. So talking about doing your experiment more than once, you want to repeat it a lot of times. And so after 6 years of running, we had smashed our particles together 1 billion times. To be able to study things that happen really infrequently. And we've done it a lot more since 2006. So my detector is 4 stories tall. Here's, you can see somebody working on it for scale reference. About 40 feet long, weighs about 3,000 tons. And this is the accelerator beam pipe. So they're actually, it splits into two pipes where the two beams are, because they're going in opposite directions. They're two separate pipes. Most of the time around the ring, but we want them to collide. So we need them to join into one pipe where we want them to collide and detect what comes out in the collision. So you'd have one beam going in this way, another one is coming from back here and going the opposite direction, and they collide in the middle. The screen thing is a magnet. The reason we have a magnet is to measure electric charge and momentum, so of produced particles. So if you've studied electromagnetism in physics, the Lorentz force F equals QV cross B. So like the charge times the velocity times the magnetic field, and it's a vector product, the velocity vector product with the magnetic field. And the charge was out front. So we basically, the way it bends, if it curves one way versus the other way as it's traveling, that tells us if it's a positively or negatively charged particle. And if it goes straight, it's neutral. And then we can get the momentum of the particle by the radius of curvature in that magnetic field. So we see how much it curves in the magnetic field. So if it has lower momentum, it's going to be a tighter curve. If it has a higher momentum, it's the same magnetic field. We know the magnetic field strength because we set that. Then it's not going to curve as much if it has more momentum. And so that's how we measure the momentum of charged particles, using how they curve in the magnetic field. We could also have detectors to measure energy. I'll talk a little bit more about those in a minute. And we have ways of measuring particle type. So this is creating a magnetic field. This is already a detector that helps us determine if a collision even happened. So a lot of the time, the protons just miss each other. We have about 10 to the 11 per bunch. The beams are not continuous. They're bunch structures. They're basically, if you think of an electromagnetic wave, it's radio frequency, or well, so if you think of an electromagnetic wave, basically the particle, all the protons get bunched up in the buckets, in the minima, the troughs of the wave. And so we have this bunch structure to the beam at about 10 to the 11 protons per bunch, and 10 to 11 protons in the bunch in the other beam, and those bunches pass through each other. And a lot of the time they can, like, everything misses because we try to focus, or the accelerator physicists try to focus the beams as much as possible, but the beam width is still a couple hundred microns. So a micron is 10 to the micrometer, 10 to the minus 6 meter, and there we have a couple hundred microns is the beam width. So it's like 10 to the minus 4 meters. And remember, the proton is 10 to the minus 15. So we have 9 orders of magnitude difference. So again, even though you think a 200 micron beam spot sounds like it's a really dense beam with 10 to the 11 protons packed in there, but the protons are so tiny in that they still mostly miss each other. So we have some detectors that just look if anything happened, if anything hit. And then we have these arms with different layers to measure charged particles, to measure charged particles and where they went, so we can connect the dots and see the radius of curvature and just if it went that way, if it was positive or negative charge. And then detectors out here that measure the energy. And then this is open for maintenance. So this would normally be pushed in on these rails down here. So the whole thing would sort of close. And we do have there's even more equipment. There would be a second magnet here that's not in the picture. That's for measuring particles that go closer to the beam pipe when they're produced. So I said I'd talk more about spin, since that's a lot of what I work on is spin and spin momentum correlations in the proton. So spin is a quantum mechanical property of fundamental particles or combinations of particles. It's called spin because it's a type of angular momentum, and it's described by equations treating angular momentum. The units of angular momentum are the same as Planck's constant, h bar, and can only have values that are integer, so 0, 1, 2, 3 times h bar, or half integer, 1/2 h bar, 3/2 h bar, 5/2 h bar. These are quantized. This is one of the things about quantum mechanics. That spin is a quantum property. And quarks and protons have spin 1/2 h bar. In a magnetic field, different spin states have different energies, but have the same magnitude of the angular momentum. And proton spin is actually what makes the medical diagnostic technique of MRI, magnetic resonance imaging, possible. So my one of the discoveries I was involved in was that the gluons make a significant contribution to the proton spin. So it's not just the quarks the quark spins that add up to the proton spin. We discovered people knew that it wasn't just the quarks it was a big surprise in the late 1980s before I was doing physics. But they haven't understood what else is contributing. And so the proton spin, the gluons are also contributing. This was a press release in 2014. This made it into Scientific American also. Here's another article. So the Phoenix experiment finished taking data in 2016. We are currently building another experiment at the Relativistic Heavy Ion Collider. That's called S-Phoenix, S for super, although I wasn't crazy about the name, but I got outvoted. It's going to start taking data in 2023. And my research group at Michigan tested more than 20,000 devices called silicon photomultipliers for the S-Phoenix calorimeter. So a calorimeter measures energy. So it's like a calorie meter, right? That's what the etymology of the word is. And yeah, we were doing this from June 2019 to March 2020. And we were super lucky that we finished this work in my lab at Michigan, like March 6th, right before the pandemic hit. Since I'm running out of time, let me move a little more quickly. My other facility is the Large Hadron Collider in Geneva, Switzerland. It's a 27-kilometer ring that goes across the border between France and Switzerland. There are about 10,000 scientists total that are on 4 different experiments. The detector itself is about 100 meters below the French countryside, and we collide about 10 million proton. We have about 10 million proton-proton collisions per second. So the Large Hadron Collider also has beams of protons, but we can't polarize them there. We can't control the spin direction of the beams there. So that's a unique capability in the US. It also runs nuclei similar to the relativistic heavy ion collider. However, the collider runs at higher energies to focus on searching for new particles rather than studying the proton and the strong nuclear force. So there's just a small group of us who are doing that there. And I was fortunate enough to be able to go with my family last November. So here I am with my kids underground, 100 meters underground at the Large Hadron Collider beauty experiment. So I just wanted to acknowledge the different group members, my postdoc, PhD students, undergrads, and so visiting scholars. Here we are pre-pandemic. This is summer 2019, and here we are. We did manage to meet. We just met once since everything started in August. So I wanted to say a few words on my path from high school. So for high school science and math, I took AP Physics B with the no calculus 1, AP Bio, AP Calc BC. My high school didn't have AP Chem or other AP Science or math courses. I was in the math club from 7th to 12th grade. In college, I double majored in physics and music, and it's really fun. I teach a course now on the physics of music at the University of Michigan. I didn't have my first research experience until college, so I didn't do any research in high school. It was the summer after my freshman year in college, and I actually worked in an experimental nuclear physics lab on campus. This was really how I got started in nuclear physics. And my first research advisor suggested I apply to summer programs at national labs. So after my sophomore year of college, as I mentioned, I got an internship working at the Relativistic Heavy Ion Collider at Brookhaven National Lab. There is now a program for that. It wasn't officially in place at the time, but if you're interested, once you're in college, this is something you could look into. And my research advisor at Brookhaven National Lab, who had German citizenship, suggested I apply to the CERN, the European Center for Nuclear Research in Geneva, summer student program. So the summer after junior year, I was fortunate enough to be selected as one of the first 10 American students in the program. It just was total they'd never accepted Americans before because the US hadn't really participated enough in the activities of CERN. It's really a European lab, but the US was getting more involved. And so it was the first time they let Americans into the program. And I got to do that, which was really, really a transformative experience. I also met my husband there from Italy. The program is still going on. It's through the US National Science Foundation, and it's one of their international research experiences for undergraduates. So they have a bunch of ones in the US and a handful that are international. And it's across the sciences, actually. So again, once you're in college, this would be something to look at, whether you're in physics or chemistry, or it's really across the sciences. And from there, I continued in experimental high energy nuclear and particle physics, doing other research projects during college, and then pursuing a PhD. But I did want to say that that might all sound very nice and impressive, but it was not always smooth sailing. So this is my first semester college physics midterm, and I already knew I wanted to be a physics major. And you can see I didn't do very well on the exam. I got a 32 out of 100. And I was really a straight A student in high school. So I just started as a freshman in college, and this was really a big shock. I realized, I still, I don't know if you keep your exams. I still have my my exam book. I realized it was 25 years ago this week, October 18, 1995. This was a pretty big setback, wanting to go in and be a physics major, but I worked really hard and I was really proud of my B at the end of that semester. And I stuck out, the second semester freshman year and got a B again, although not quite. It was a little bit more of a steady B rather than a fail, moving up to a B for the second semester. I also actually left my first PhD program, and the immediate cause was health problems, but I had been treated very badly by 3 individuals there. And that, was a huge change in plans that really threw me off in my early 20s. I ended up following my then boyfriend, now husband, to his home country, teaching English and music in Milan for a year and a half before finding my way back to physics. So in closing, even though protons are a fundamental building block of everyday matter, we still have lots to learn about the complex behavior of the quarks and gluons inside them. High energy particle accelerators allow us to probe the structure of very tiny objects. And a community of a few thousand people around the world is working to unravel the mysteries of the proton and the strong nuclear force that holds it together. And I just like to say that, nonlinear paths towards one's goals are a lot more common than you might think. So try not to be afraid of setbacks or changes in direction. Thank you.
Thank you so much. I'm inspired by your stories. Oh, I don't know if you know this, but like there's like this like almost like a joke where there's a person and he has like his assume he like in his mind he has a plan, right, about how his life is going to be, right, and it's like a straight line, and then the reality is actually, oh wait, can you hear me or not? Oh
Yeah,
yeah.
I can hear you.
Yeah, the actual reality is that it's like super bumpy and like there are mountains and like puddles and like all in the way. And it's kind of like how life is actually really like, which is like also like for students who right now, like me and all the others who are like sometimes you struggle at school, sometimes school's pretty fun, sometimes easy. Like I guess it gives some perspective on how life is actually going to be like further in the future for us, because like you talked about your whole physics thing, right? So some kids might have setbacks back then, but like look at you now, right? You're in like CERN and you're doing all these such cool things. So like I guess it gives to like to say that it's not going to be, it might be better, it'll be better in the future type of thing.
Yep. Keep making a plan, adjusting a plan, and
Yeah,
moving towards your latest goals and maybe redefining them, etc. So
yeah. And so then I also have a question about CERN, specifically. In CERN, because I know there are like so many people working on it at a certain time, right? um, how are the logistics of it like brought out, and how can you like mobilize so many people? Is there like, what is like the structure to certain?
yes, so to get these new facilities built, you have organized long-range planning processes in the communities, like every 5 to 7 years, typically. So um, to prioritize to talk about what are the different proposals, what are the different ideas, and what are the community's priorities, and that ends up being advice to governments, basically. And then once you have a facility that is being built or already built, you end up with, yeah, if you're in a 500 or 800, like my collaboration at CERN is like 850 scientists, you have a lot of structure. I mean, you need to have rules, usually called bylaws, so collaboration policies, who's allowed to be an author, what are the requirements, what's the requirement. You can't just do analyze the data and then just go show it by yourself. There's a whole approval process that you have to go through where it's reviewed, et cetera. So you have, I mean, for any kind of organization that gets bigger than, I don't know, a couple hundred people, you need some kind of structure and policies.
So being also a government organization, right? Because it's a bunch of governments working together with their scientists.
Mhm.
It's quite. Would you say it's quite bureaucratic in that sense?
CERN, yeah, CERN has a fair amount of bureaucracy in that sense. Yeah, well, I don't even know a lot of the details, but they're different, there are a bunch of member states and then associate member or associate. So the US is not a member state, so it's mostly European countries that are member states of CERN, and then they have quotas for financial contributions. So it sometimes is in just the form of money, sometimes it's in the form of equipment, and there are all these negotiations about yeah, how the different governmental funding agencies for science in the respective countries are going to contribute their agreed upon share.
Also, like I like your pendant, like the golden
Oh,
ratio pendant.
thank you.
Really cool. Yeah. Does anyone have any other questions other than me? You can put them in the chat or ask them anything about, any questions on how can I get into working with you, or like how can I do stuff like this type of thing. If or anything about her speaking or work. Does anyone have any questions? I guess we'll have to wait a little bit. But yeah. It's really cool that you you broke the record for the heat for all the highest temperature ever created, right? That was really cool. Oh, and then also I was discussing with a friend about that. Is it safe to do that? Would it like melt something, or like how's it contained? Is it?
Yeah, so remember the distance scales we're talking about. So we were
Yeah.
achieving this by colliding two nuclei. So we did it by colliding two gold nuclei, and a year later we were beaten by the Large Hadron Collider colliding two lead nuclei. So it's the volume is the volume is of order 10 to the minus 14 meters.
Oh, so it's really small. It's really small.
Right, because it's just right the
Yeah,
cross-sectional area of these, of the two nuclei colliding.
Yes. So it's a small scale, and it's also for a very small amount of time, actually. So the reaction, like the whole thing happens in like almost not even a blink of an eye. It's really tiny time. So I guess it doesn't affect anyone. Yeah.
Right. It cools off right away. We see the photons that are emitted when it's hottest. Well, we see photons also as it's cooling, but then we go and look at what the hottest ones are, or what the highest energy photons are, corresponding to when the temperature was the hottest. And then we also look at all the bound state, the quarks, as a fraction of a second after this really high energy density, really hot matter plasma is formed, it's immediately cooling, right? Because we're not putting any more energy in. So it's expanding and cooling, and the quarks and antiquarks end up forming bound states. And then we see those bound states, and we see these thermally radiated photons that are analogous to like the orange light coming off your hot metal.
Oh, okay. So that's how you check it. Yeah, that's really cool. So also I have a question about the computation aspect. I know there are so many scientists, but in certain, do they ever apply computational techniques like machine learning or statistics and all these things? And what would they use them for specifically, and what the applications of what you do?
So yeah, all the measurements we do involve statistical analysis, right? So we're analyzing millions or billions of events and looking at statistical properties of the data and testing consistency with different predictions and incorporating statistical uncertainties on the measurements that we make. And then everything we do involves a lot of our data scale, like volumes or petabyte scales of data that we're working with. Yeah, we use. I mean, I do have a couple, servers for my own research group at Michigan, and sometimes we work with really tiny sets of the data to do local, like develop our code to analyze the data on local machines. But then when we want to run over the full data set, once we've sort of debugged on really small samples that we bring over locally, then we have to run on big computing farms at CERN or at Brookhaven National Lab. You have to get a computing account, computing credentials to be able to.
Yeah, that's really tough.
And do that. And in terms of machine learning, yeah, there are a lot of machine learning techniques used. I sometimes think they're overused by physicists. People get a little too excited about being able to use novel tools that they think are interesting. Because a lot of them you lose transparency of what's really going on, right? What are the
because of the black boxing.
Yeah. So I mean, at least the neural network techniques. So boosted decision trees are more transparent. That's one of the machine learning techniques that my group works with, boosted decision trees. And I like it better than neural networks because it is more transparent. You can understand what criteria are being used to decide something belongs in one category or another. So we use them. For example, one of my grad students is using boosted decision trees to determine if a spray of particles that we observe in the LHC-B detector was initiated by a charm or by a light, like an up, down, or strange quark. Any of those, we can't tell the difference, but what we call those light quarks, like as in mass. A charm quark or a bottom quark, beauty quark, I guess, bottom or beauty. So yeah, there are different features of the sprays of particles, and we have ways to categorize that we use boosted decision trees for.
And also, I was gonna ask a question about the research, like the findings of your research. What can it be applied to usually? What would it be applied to usually in terms of like actual like industry things? In terms of like, is it purely theoretical to the sense? Like, is it just stuck there, or is it like more?
Well, I wouldn't call it's experimental, so it's not theoretical, but I think what you
Yeah.
mean
Oh yeah.
is often called basic research, so as opposed to applied research. What I do is basic research. A lot of our the technology developed from how we develop our new detectors, sometimes computing techniques and things like that end up having applications in the shorter term often. So actually, yeah, I don't know if you know, but at CERN, it was due to the particle physicists working at CERN in the 1990s that the World Wide Web was developed, was
Oh
invented.
yeah, yeah, yeah. I remember because of the communication between them and all these things.
And
Yeah.
so, I mean, yeah, so just like network communication was developed by the military in the US, as far as I know. But the World Wide Web, so having like the idea of browsers, so that having this interface that people could work with was developed at CERN by particle physicists, and so that is a huge application. But
Yeah.
it wasn't the physics that led to the application. Just I mean, that was the 1990s, so of course the World Wide Web was a thing being used by millions or hundreds of millions or billions of people just a few years after that, right? By the late 90s. Yeah, the longer term, a lot of proton spin is used for nuclear magnetic resonance, right? But that took more time though
Oh yeah.
to turn into an application. So if people didn't discover the proton back, 100 years ago, and then understand that it had this property called spin and how that property interacts with magnetic fields, and that happened all over a few decades in the 20th century, that led to the medical technique of nuclear, we call it nuclear
NMRs.
MRI,
Yeah.
magnetic resonance imaging.
Yeah. That's
But
really cool.
it does lead to applications. I know actually some of my colleagues who work with polarized helium. They were working originally with polarized helium targets to study polarized neutrons. Polarized helium-3 in particular. So two protons and a neutron, and they wanted to understand spin properties of the neutron. And so they were working with polarized helium targets, and then they ended up going into medical applications. Actually, not so long. I mean, yeah, within the last I don't know. It didn't take that many years to lead to medical applications using polarized helium-3 to basically image the lungs. So it's helium is a noble gas, so it's inert enough. You can breathe in helium and you get your helium voice, but it's safe to put some in the lungs. It doesn't react, and then so you can put this polarized helium in the lungs and do certain kinds of imaging with in the lungs using polarized helium. So some of my colleagues who worked on polarized helium-3 originally to study the internal structure of the neutron were able to develop this into a new medical technique that's already used. But it wasn't, the medical technique that was developed wasn't related to understanding the quark structure of the neutron. It was related to the technology of developing, working with polarized helium.
Oh, okay, okay. I see what you
So the
mean.
basic research, the quark gluon structure of the proton, like what I'm doing to turn into an application, the two kinds of applications that I might imagine, like after, maybe I'll see them like after I retire in my lifetime, or things going in that direction, but maybe not. So it's sort of decades away. But I could imagine having like what I'm studying leading to more efficient fusion energy. We don't even do fusion energy now, as
Yeah.
people are working on it, but it's not a viable energy source right now. But I could imagine understanding better the quark and gluon structure of the proton and the neutron, leading to more efficient fusion and potentially leading to more efficient fusion energy in the coming decades. And I could also imagine things that were more like nuclear printers, that you could produce different types of nuclei on demand on tabletop scales. Right now, we can do it really inefficiently on like building size scales. So Yeah, so it's called isotope production. So to make a nucleus with a specific number of protons and neutrons. So there are different facilities we do this for certain like medical nuclear isotopes for different medical procedures, radioactive isotopes used for medical procedures. There are accelerator facilities that make those, but they're pretty inefficient and they're building sized right now. And so, maybe understanding better the quark and gluon structure of protons and neutrons would allow you to make that more efficient because you could really, like, um, it's only a small fraction of, like, accelerate something, smash it into a different nucleus, and then they know that, okay, yeah, like 5% of what comes out is going to be what we
Is the
want.
resultant.
Yeah,
Wow.
right. And then the other 95% we just have to throw away because it's not useful or whatever. And so maybe, what I'm studying could eventually make that more efficient. So we can do that more efficiently. And as things miniaturize, if it became tabletop. So that's the other thing I can imagine. But it's not my career. It would be decades away.
Yeah, it's kind of like, how like computers were so big back then and now they're like tiny. You can have them in your phone, miniaturization, so much. Yeah, I don't know, in my lifetime, maybe. Okay, so it's 2:59 and this talk is coming to an end. Thank you so much for actually speaking with us and coming here. And we're really grateful for you to, to talk and explain and share some of the knowledge you have with us. And especially for me, thank you so much.
Okay, thanks so much for having me.
Yeah, and just a really big thank you on behalf of STEMI as well. There's so many, like, such incredible research that you've been doing, and it's really an honor to get to hear about it from, even the comfort of my own room. That's really spectacular.
Thank you.
All right, let me just get our next speaker event set up. Awesome. So right now it's 3 o'clock, so we're going to start our next speaker event. And yeah, just before you do, please thank Dr. Aidala for coming out with and speaking with us today. Now we're going to transition. I'm going to let Claire reintroduce STEMTober for any of you who just joined and didn't get to hear about the entire event.
All right. Okay. Welcome, everyone. Hope you are all excited for another STEMTober speaker panel. So STEMTober is hosted by STEMI and Wave Learning Festival. STEMI is a nonprofit organization that hosts STEM classes and events primarily for high school students, and Wave Learning Festival is a nonprofit educational platform that offers free courses for middle and high school students by college students in an effort to improve educational equitability. So for those of you who are just joining us, every Saturday in October, we've been focusing on different STEM fields for interested students who may not have had much exposure to STEM to explore. So weekend 1 was all about engineering, and weekend 2 was focused on computer science and math. Weekend 3 was on medical field and healthcare, and this week, weekend 4, is about physics and chemistry.
Awesome. So our next speaker is Dr. Pandilas. Please welcome him from Vanderbilt University. He was named the Fellow of the Institute of Electrical and Electronics Engineers in 2015 for contributions to point defect dynamics in semiconductor devices, and is a University Distinguished Professor of Physics and Engineering. And just before I forget, let me